Hello, welcome back. Hello, welcome back. We're going to look at some special binary trees. First, we see what is called as proper/full binary trees. Let me give a few examples of it so that you understand what are full binary trees. This is a binary tree with one node, that is, there is only a root node and it's a full binary tree. This is also a full binary tree. So there is root node and two child nodes. Okay, so as we know, a binary tree, every node in a binary tree has at most two children. This is also a full binary tree. Okay. Let's look at a few non-examples. Examples of trees, binary trees, which are not full binary trees. This is not a full binary tree. So this is a binary tree where the root node has one child, exactly one child. So do you see what is full binary tree? A full binary tree is a binary tree where every node has either two children or zero children. Okay, so every node has zero or two children. So this is an example where this is not a full binary tree because here the root node has one child. Here is another example. This is also a node which do not have two or zero children for every node because there is one node, especially this node, which has exactly one child. So another way to write this is a full binary tree is a tree where no node has one child. That's another way to write this. The next tree we are interested in is called as complete binary trees. In a full binary tree, we saw that there cannot be any node with a single child, right? Okay. In a complete binary tree, what we are saying is that the depth of every leaf node should be the same. That's the definition. Depth of all leaf nodes should be the same. Okay. Let's see a few examples. First example is a node with a tree with one node. There's only a root node, and obviously this is a complete binary tree, right? Because there's just one node and its depth is zero. Next, this is another example, right? So you can see the depth of all leaf nodes is the same. is 1. Here's another example. The depth of all leaf nodes is the same, which is equal to 2. Do you see the pattern? What will be a complete binary tree with the depth of 3? Which is the complete binary tree of height 3? So this is a complete binary tree of height 3. Good. Can you give me examples of binary trees which are not complete? How about this? This is not a complete binary tree. Why? Because there is a leaf node. Consider this leaf node. What is its depth? 1. Consider these two leaf nodes. What are its depths? 2. Okay. So we want in a complete binary tree, depth of all leaf nodes should be the same. Okay. Now let me pose to you two questions, two algorithmic questions. I give you a binary tree as input, so you have to write a function which takes as input a binary tree and answers whether it's a complete binary tree. Can you do that thing? Think about how to write an algorithm which can take as function a binary tree and outputs, checks whether it is a complete binary tree or not. So it's going to return true if it's a complete binary tree. The function returns false if it's not a complete binary tree. How can I write that? Similarly, another function you can write is write a function which checks whether a tree is a full tree or not, a full binary tree or not. Can you write a function for that? You get the question? Yeah. Okay. So this is what will be a hint I can give you? How can you write this? So you can use a recursive algorithm to check for this fact. Okay. Yeah. Good. First of all, so why am I saying recursively? Because first of all, a binary tree is complete if, let's say, its left child is a complete binary tree and the right child is a complete binary tree, right? You have to recursively check these two facts. Left child is a complete binary tree, right child is a complete binary tree. Second thing you need to check is the height of the left child should be equal to the height of the right child. Okay, so if you check these two properties, you can see that it is a complete binary tree. Okay, so why don't you write a function to do this? Okay. Now, so you can write a recursive function to do that. Now let's go to let's see some properties of complete binary trees. What is it? Something I would like to ask is we saw that a complete binary tree of height k is fixed, right? Because we just now saw that how to draw a complete binary of height 2. We saw how to do it, and that is this is that tree. What is a complete binary tree of height 3? This is the tree. Complete binary tree of height 1, here it is. 0, here it is. So these are all unique. There's exactly one complete binary tree of a particular height. Okay, good. Now I can ask a further question. If I give you a height h, how many nodes will be there in a complete binary tree of that height? Okay, so how many nodes are there in a complete binary tree of height h? So let's see some few examples and decide what can be the formula for it. So here h is equal to 0 and how many nodes are there? So I'm going to n is going to stand for the number of nodes and h is going to stand for the height. This is 1. And here it's going to be h is equal to 1 and n is equal to 3. Here h is equal to 2 and n is equal to 4 plus 3. 7. H is equal to 3 and n is equal to 7 plus 8, 15. Do you see some pattern? Okay. So let me write the answer. N is equal to n is equal to 2 raised to h plus 1 minus 1. I claim this is the answer to the question I posed. Let's see some examples. Okay, let's plug the value of h in all these examples. What about if I plug in h is equal to 0? It becomes 2 raised to 0 plus 1, 2 raised to 1, 1 minus, 2 raised to 1, 2 minus 1, 1. N is equal to 1. It's correct. Plug in h equal to 1. It becomes 2 raised to 2, 4 minus 1, 3. It's again correct. Plug in h equal to 2, 2 raised to 3, 8 minus 1, 7. Correct. H equal to 3, 2 raised to 4, 16 minus 1, 15. It's also correct. Okay, so this seems to be working fine. How do you prove this fact? Again, we can use mathematical induction to prove this. I can just show you. Okay, here is a way to prove it, right? So I know the base case. Okay, so this will be part of a discrete math course, so I won't go into the more details and elaborate thing. I will just give you a brief idea. So the base case, the formula is true for the base case of the inductive step, that is the base case is h is equal to 0, right? And there it's correct. We are going to induct on the height of the tree. Okay, and so induction on the height of the tree. Okay, and we know the base case. So here this is correct, right? Because we know that in the base case n has to be 1 and n is 1, because when I plug in h is equal to 0 in this formula, it's correct. It's turning out to be 2 raised to 1 minus 1, 1. This is correct. So I'm going to tick this, that the base case works fine. Now let's look at the inductive step. So inductive step, I'm going to assume that the claim is true for up to height, let's say less than or equal to k, the claim is true. I'm going to assume, so let me note this down. Assume claim true. Okay. Assume claim true for h less than or equal to k. Okay. Now, using this assumption, can I prove for k plus 1? So that's how induction works. I'm going to use this to prove that the claim works for k plus 1. What is it we are going to do? I'm going to just consider this tree. Okay, so I just draw a tree, and I'm showing you only the root tree and its two subtrees. Okay, so there's a left subtree and there's a right subtree. Okay, and assume we are going. So I have taken a tree of height k plus 1. Okay, so the root height is k plus 1. So what is the height of this subtree? It's k. Height of this subtree is also k, right? So what are the number of nodes in this left subtree? We know that since the induction hypothesis holds, we know that the number of nodes in the left subtree is 2 raised to k plus 1 minus 1, and the number of nodes in the right subtree is also 2 raised to k plus 1 minus 1. So what are the total number of nodes? The total number of nodes in the entire tree is the number of nodes in the left subtree plus the number of nodes in the right subtree plus the root node 1. You can just write, let's just sum that up, right? So this is 1, which is for the root node, plus 2 raised to k plus 1 minus 1. We add it twice. Right? Because I have two subtrees, so I have to add it add it twice. So this guy gets cancelled, right? 1 minus 1 and a plus 1 gets cancelled. Now what is remaining? You have 2 times 2 raised to k plus 1. Okay. Right. So what is that? That is 2 raised to k plus 2 minus 1. So and there is a minus 1 remaining. So this becomes equal to 2 raised to 2 raised to k plus 1 plus 1 minus 1. Okay. It's clear. This is exactly what we wanted, right? Because we just now showed that for a height, um, what we wanted to prove was that if I plug in h is equal to k plus 1 in the formula, we are done, right? That's what our answer our the answer we are claiming is that if I plug in h is equal to k plus 1, that gives me the number of nodes in the tree. That is 2 raised to k plus 1 plus 1 minus 1 was supposed to be the answer, and that's exactly what we proved right now. Okay, so this is good. This is all good. We have now argued that the number of nodes in a complete binary tree is 2 raised to 2 raised to h plus 1 minus 1 if h is the height of the tree. Now I ask you another question. Now let me ask you another, let me turn this question upside down. If I give you the number of nodes in a complete binary tree, what is the height of the tree? You understand the question I'm asking? If I give you the number of nodes in a complete binary tree, what is the height of the tree? We go back to our equation, right? The equation we had was n is equal to 2 raised to h plus 1 minus 1. And I want h in terms of n. What should I do? You take log to the base 2. Let's try to take log to the base 2. So I'm going to bring in minus 1 to the left. So that becomes n plus 1 is equal to 2 raised to h plus 1. Take log to the base 2 on both sides and you're going to get h is equal to okay. This is our height. So in many cases, whenever I'm going to use log, I'm going to assume it's log to the base 2. So I won't carry this 2, the base 2 around. Okay. So usually in computer science, whenever you write log, it's to the base 2. Okay. This is how we will write usually. There are instances where the natural logarithm will also be useful. So in that case we will specify that it is we are taking the natural logarithm to the base e, for example. And here we have taken the log to the base 2. Okay, so now if someone asks you the question of, someone gives you the height of a uh, someone asks gives you the height of a tree, and you are supposed to tell how many nodes are there in a complete binary tree, you know the answer. That is 2 raised to h plus 1 minus 1. Now, but if someone also asks you another question on, he gives you the number of nodes in a complete binary tree and asks you what is its height, you know the answer, log of n plus 1 minus 1. Right, so these are good things. Now, so what? Just think about it. Why did I call this binary tree as a complete binary tree? Because that's kind of the, like the biggest binary tree of that particular height, right? If for a height h, there is no other tree of height h which contains more nodes than this complete binary tree. This is the maximal binary tree of a particular height. That's why it's called complete, right? This is clear. It's clear, because if you can't add a node anywhere in a complete binary tree without violating two properties. So if you add any extra node in a complete binary tree, it's going to either increase its height or it's going to it's not going to be a binary tree. You'll have to add the node as a child of a node which already has two children. So the number of children of that particular node will become 3, and therefore it's not a binary tree at all. So, clear? So you will have to, if you can't add any more nodes to a complete binary tree of height h without violating one of these two properties. Either you increase the height h or you increase the number of you or it's no longer a complete no longer a binary tree. This is you get a picture. No. So what I'm going to is the fact that the number of nodes in a complete binary tree is the biggest among all the trees of that particular height. Okay. Therefore, I can write the following claim. I'm going to write a particular claim. I'm going to write that. So here is my claim on about general binary trees. Okay. For any binary tree, n is the number of nodes in that binary tree is less than or equal to 2 raised to h plus 1 minus 1. Okay, so what am I saying? The number of nodes in any binary tree is less than or equal to 2 raised to h plus 1 minus 1, where h is the height of that binary tree. Okay, is that clear? Why, I mean, just recollect, why can we say that? Because we know that a complete binary tree has 2 raised to h plus 1 minus 1 nodes, and that's kind of the maximum possible. So any binary tree which has a height h should have at least that much, then it becomes a complete binary tree, or less than that many nodes. Right? So this is why we can write that any node, any binary tree having n number of nodes and height h should satisfy this equation that n is less than or equal to 2 raised to h plus 1 minus 1. Okay, how do I state that in terms of h? Okay, so in terms of h, this becomes h is greater than or equal to log n plus 1 minus 1, right? Okay, so these are very important inequalities we have to keep in mind. Okay, if you don't keep in mind, you will have to work it out from the basics, right? Okay, but this will be very important, right? Okay, thank you.